So I continue with section 3. First of all, Chris, I think everybody else I told there is a misprint on the third exercise sheet, so this formula 2 should read like this. So what did we define last week? Given a Lie algebra L over a field F and a vector space V over the same field, we defined a representation of L on V or equivalently, there is just another terminology, which is an L module structure on V. And that's simply a homomorphism of Lie algebras. From this Lie algebra L into the Lie algebra of linear maps from V to V. So, and now we learn some usual algebraic constructions. So this is a bit boring, but we have to go through this. Namely, first thing is a submodule. So if V is an L module, and then we consider a vector subspace say W of V, and this is called a submodule or subrepresentation. If the following holds, for any element X of the Lie algebra, and for any vector V which is contained in this subspace W, XV is still contained in W. And recall we always switch between these two notations. So here I use module notation. Equivalently, I could give a name to this structure map, say phi. And then what this formula actually means, for each element of the Lie algebra, we get an operator phi of x on V, and I apply this operator to the vector V, and the resulting vector should still be contained in W. Yeah, let's have a look at an example. we consider the vector representation of a linear Lie algebra, namely this Bn. So this was the Lie algebra of upper triangular matrices, say in with coefficients in doesn't matter. So sub Lie algebra of GLN F, arbitrary field, and we have this sub Lie algebra of upper triangular matrices, and vector representation means that acts on F to the n just by matrix vector multiplication. So I need to consider a subspace W, and this is just the space generated by the first R basis vectors for some R from, anyway, some R. So then W is a submodule. And I hope this time I got it right, so I have to take an initial sequence, not a terminal sequence of indices here. And the proof is very easy. So what does well, we have to pick an arbitrary matrix which is contained in Bn. So this has the form, some upper triangular matrix. Then we have to apply this to a vector which is in W. So there is an initial set of stars here, also of arbitrary components, namely first R components may be arbitrary and all the others are 0. So and if you do the matrix vector multiplication to compute the last entries beyond the first R entries, you notice that you have to form this cross product, and for the first summons this factor is 0, and for the last summons this factor is 0. So again we get zeros here and some arbitrary thing here which we don't care about. So this is still contained in W. So this is the first example of such a submodule. Why is this called submodule and not just invariant subspace or something? This is the following observation. We consider such a submodule of an L module. And then W itself becomes an L module. Why? Well, I have to define the operation, the structure map. Well, and this, it looks kind of stupid. So I have to define xv, if x is any element of the Lie algebra and v is any element of the subspace. And I just define this to be xv, where, of course, here the implicit operation is the L module structure on V. So anyway, It's a trivial thing, but maybe you should think about it for a second. Yeah, now we define submodules. Of course, we have also quotients. So I indicate this also briefly. So again, we consider a submodule of an L module. And then we consider the quotient vector space V mod W. And this becomes an L module also. So I have to write down the structure. We'll pick an equivalence class V bar. And an element X of the Lie algebra. This must be another equivalence class. Well, and just pick a representative V of the original equivalence class. Compute XV, so this is again implicitly the L module structure on V, and take the equivalence class of this. So and then note and definition. So the quotient vector space with this structure is called the factor quotient or factor module. Of V. We also I have to show that this actually defines a L module structure on the quotient vector space, and the crucial thing here is the well-definedness. So, well, this kind of arguments we've seen in the exercises also, but let me just do it for the sake of completeness. So we have to show that this product is well defined. So we fix an element of the Lie algebra, and V1, V2 representatives of the same class. So I have to show that xv1 is in the same class as xv2. In other words, that the difference xv1 minus xv2 is contained in W. If the difference is contained in W, then xv1, xv2 are in the same class mod W, so this definition makes sense. Well, but X, remember, if I write xv1, this is just short notation for 5x. 5x, so this are linear operators. So I use the linearity here and get x v1 minus v2. So by assumption, this is an element of W, and by definition of a submodule, x times an element of the submodule is still contained in the submodule. Okay, so the fact that these axioms are then fulfilled, that this is a homomorphism of Lie algebras, is then clear. Rest clear, or exercise if it's not clear to you. So we have these two notions of a submodule and a quotient, and so if we've given an arbitrary L module V, which has a submodule W, one would try to, or one could try to study the complete module by studying the submodule and the quotient module. These, in some sense, the total module is built from the submodule and the quotient. So the atomic modules are those which don't admit such a submodule, and these are the first ones to study. So more precisely, given such an L module V, we say this is irreducible, or simple. So these are two words which are used for the same thing. Well, if there are two conditions, first is V must not be the zero vector space itself. And the second one, we fix any, or choose any submodule W. Then this must be either the trivial vector space or the complete thing. These two, of course, are always submodules, so these are the trivial cases to exclude. And well, as I said, if there are intermediate submodules between 0 and V, then one might try to reduce the study of V to the study of W and the quotient. So somehow it's natural to start by, or it's natural that these have some importance. Good. Some examples. So the others I call reducible, because it's kind of stupid to say not irreducible, so otherwise V is reducible. So, trivial special case, if I have a module such that the dimension of V as a vector space is 1, we know any submodule is in particular a subvector space. So a subvector space of a one-dimensional vector space is either 0 or one-dimensional. If it's zero-dimensional, it's 0. If it's one-dimensional, it's the whole thing. So even without thinking about the Lie algebra, we know that any such module is irreducible. This is a bit boring, but I recall in this exercise 2.3, you showed that if L is this vector product Lie algebra, then L has only two ideals. Namely 0 and L itself. So, and I can reformulate this property as follows. Recall that we defined the adjoint representation of L on L. Here, L acts on itself by bracket operation from the left. And this is irreducible. Yeah. So recall the adjoint representation was given as follows. I pick an element of the Lie algebra and an element of the vector space, which is also the Lie algebra in this case, and this was defined to be the Lie bracket. Yeah, proof. Well, suppose we have a proper non-trivial submodule W. And we have to show that this is a contradiction because we want to show that such does not exist. Yeah. So, what does this mean? It's a submodule. So, for all elements of the Lie algebra X and elements V W, at X, V is contained in W. The definition of a submodule. But this is just the bracket, X and V. So we've shown whenever I pick an arbitrary element of the Lie algebra and an element of this vector subspace, then the bracket is still contained in the vector subspace. So this is just the condition of W being an ideal. Yeah. So, but you showed that there are no proper non-trivial ideals in L, so this is a contradiction. Yeah, the rest of the lecture is about one example, which is particularly important, so it gets its own number. So far, this was still chapter 7 of the book. This is chapter 8 in the book now. You recall we studied this Lie algebra, and we defined the Lie algebra SL2C. And this is the set of all complex matrices with trace 0. And we showed that this is a Lie subalgebra of GL2. And we've already seen also this basis. Consisting of the following matrices: E, F, and H. And you also already computed the pairwise commutators. Commutator of E and F is H. Commutator of H and E is 2E. And the commutator of H and F is minus 2F. Okay, and now I'll define a sequence of representations of this Lie algebra. This is as follows. Fix an integer d, can be 0, yeah. So the first thing is to define the vector space, and the second step then to define the structure. So that's map phi. So what's the vector space? So here I use a different notation in the book. In the book they use a subscript d, but I like this better for some reason. So for the lecture we use this notation. This is the following. We consider the vector space of polynomials in two variables, x, y, and write subscript d. So that means I only want to take the homogeneous polynomials of total degree d. So this is a vector subspace of the polynomial algebra. Maybe let's write down the bases of the first couple of examples. If d is 0, then Vd is a one-dimensional vector space, for example, with basis 1. This is a homogeneous polynomial of degree 0. If d is 1, well, I just write down the monomials, and this gives a basis then. So the homogeneous monomials of total degree 1 are x and y. Now it becomes slightly more interesting. So V2 x squared xy y squared, and so on. So you see maybe the general formula already, the dimension of Vd is just d plus 1. Because always these monomials will form a basis, and the total degree has to be d, so I order them such that the degree in x is descending and the degree in y is ascending. Yeah, next step is to define the L operation. And I claim that I can define one as follows. So for any d, this vector space Vd becomes an L module. By the following associations. Now I have to define the operator by which the first basis matrix 0, 1, 0, 0 acts on the vector space, and this is x d dy. Then I have to define the action of the second basis vector. So this is just y d dx, the opposite thing. And the action of h is given by the following operator: x d dx minus y d dy. Maybe I do some examples also of the. So if I apply E to, say, a monomial x to the 2, y to the 3, so this is an element of V5. This is by definition, I have to apply this operator, x d dy x squared y to 3. So this gives 3 y to the 2. The x squared is just a scalar for the d dy operator, so this goes out and combines with this x to the 3. The y gives the scalar 3, and the 3 goes down to 2. So how do we prove that this defines an L module structure on this vector space? Maybe in 2 steps. As a first step, we show that it defines an L module structure on the vector space of all polynomials. And then as a second step, we will show that the homogeneous polynomials of a fixed total degree are invariant, so they are a submodule, so they become, by this node, also almodules. So what I do is I verify that these operators fulfill the same relations as EF and H. Well, let's just start with EF, maybe. And apply this to a polynomial P. So this was x dd y, y ddx. P. Yeah, so this is the general linear Lie algebra, so the commutator is just a difference of the two orders. So this is x dd y, y ddx p minus the opposite, y ddx x ddy p. Well, so I just computed. Here I have the product of two functions, or of two polynomials, y and the derivative of p with respect to x. So I have to apply the product rule. So first sum and I derive y. But the derivative of y with respect to y is just 1, so this doesn't do anything. And the second factor is ddxp. The second summand of the product rule. Now y remains underived, and here I take the derivative of the second factor, which is wrong, gdy ddx p. Yeah? So this is the first summand here, evaluated with product rule, minus, same thing. I derive this product of two functions. So I use product rule. First summand has a 1 here, so this is dy p. And the second summand, now x remains underived, and here we have ddx ddy p. So now there is a theorem in analysis, or well, here they are just polynomials, so here it's easy. If you have a polynomial in two variables and you derive with respect to x and then with respect to y, or if you do it first, you derive with respect to y and then with respect to x, you get the same result. And then you multiply by xy, but this is the same as yx. So these two terms cancel. And what remains is x d dx p minus y d dy p. And this is exactly phi of h. P. So the other are similar. Other relations. So I won't show all the computations with essentially the same. Just use this elementary calculus rules. So we showed that phi e, phi f, phi h fulfill the same relations, and this from this we can conclude that phi is a homomorphism of Lie algebras. Yeah.
Since when you check things, you always have to go back to check homomorphism, meaning the representation picture.
Right.
What is the advantage of having the module language? The algebraic language of having an L module.
As opposed to a representation.
Dealing with the representation.
None. None. So it's, I don't know, really the thing is, you don't, it's less work writing because you omit the phi's, but okay. In my opinion, otherwise it's really totally equivalent. And so if you don't like the homomorphism, on one of the exercise sheets I gave the I think on the one due for this Thursday I wrote down the equivalent formulation without using phi, so you can check that always. By linearity. Yeah, the thing is, of course, what do I mean when I say let phi be the map given by phi of E is x d dy, phi of f is y d dx, and so on. Then I mean let phi be the linear map. Linear map is uniquely determined by its values on a basis. So if I fix any element of the Lie algebra, then this has a expression, the basis, say alpha E plus beta F plus gamma H. for some scalars. And we'll fix the second element y of the Lie algebra. Say this is alpha tilde e plus beta tilde f plus gamma tilde h. And I have to compare phi x, phi y with phi of xy to show that these coincide. That's boring. How clear is this to you? So maybe can you raise hands who doesn't want to see this computation because it's obvious to him? No, nobody. Okay, then I'll do it. This is the property I have to show to prove that phi defines a representation. So far I only showed these three properties that the images of E, F, and H fulfill the same relations. So I claim that from this I can conclude by linearity that actually this is a homomorphism. So I just do alpha E plus beta F plus gamma H. Alpha tilde E plus beta tilde F plus gamma tilde H. So phi is a linear map, and the bracket is bilinear. So it's linear in the left argument and in the right argument. So what I can do is I can expand everything. So this gives first term times first term, alpha tilde, phi of E, phi of E. All right, so I've taken first term times first term. Then first term times second term. Again, the scalars can be taken out by linearity of phi and bilinearity of the bracket. So this is A beta tilde. And what remains is phi of F. Phi of E, phi of F, and so on. So there will be 9 summands altogether. I don't write all of them, but just the last one. 9 summons, each summand here times each summand here. So the last one will be gamma tilde phi of H. Phi of H. Well, some of these are obviously 0, but let's not think about this, but let's just use that we already showed that the images of E, F, and H fulfill these same relations. Or maybe I start from the end. We have to show that this is phi xy. So this is, again, I just expand x and y in the basis, alpha e plus beta f plus gamma h, alpha tilde e plus beta tilde f plus gamma tilde h. Now I do the same trick. I use linearity of phi and bilinearity of the bracket, just in the other order now. Now I use first bilinearity of the bracket to expand everything, and then I use linearity of phi to get the scalars out and distribute over the sum. So what this gives is alpha, well, first term times first term is alpha tilde phi of E plus, and so on. There will be 9 terms altogether, and the last one is gamma tilde phi of H. So let's compare these two sums here. Both sums have 9 summons. The coefficients coincide, because the coefficients are always, I obtained them by the same product here. And the vectors also coincide. This is by star. So yeah. I checked that the operators by which E, F, and H act fulfill the relation star. That means they fulfill the property which I require for a homomorphism of Lie algebras. And well, I didn't write all of them down, of course. Here, if I give the relations, I always assume that I know that the bracket is always alternating, so products of 2 times the same are always 0, so I don't write these relations down. And also E times F is the same as F is the negative of F times E. So there are only 3 relations written down here out of the 9 I actually need here. But well, the others follow trivially from those. So this is the same. Good. Okay, so this was step 1. So I've shown that we get an operation of SL2 C on the set of all polynomials. And, well, then I just observe that the operators, all operators preserve the total degree. Again, these were x ddy, and this reduces the degree in y by 1, but multiplies with x, so it increases the degree in x by 1. The other one was y ddx, so this reduces the degree in x by 1, but multiplies by y, so increases the degree in y by 1. So the total degree is preserved. And the second one was, the third one was x ddx minus y ddy. So both of them, with the same reasoning, preserve the total degree. So Vd, which was just the sub-vector space of homogeneous polynomials of total degree, D is submodule. Okay. Good. So we spend a lot of time on this, but actually the main property I want to show is that these are irreducible modules. So this gives actually a further example for this kind of modules. We defined earlier the irreducible modules. Well, let V be a non-trivial submodule. And of course, we have to show that W is the entire thing. Well, how do we do this? Well, if W is non-zero, there is certainly a non-zero polynomial contained in W. So I express this polynomial as a linear combination of the monomials. How did I call the coefficients? Oh, just A or alpha maybe. Alpha 1 x to the d, alpha 2 x to the d minus 1 y, plus and so on. There are some coefficients. Alpha k x to the d minus k plus 1 y to the k minus 1. Well, and either all coefficients are non-zero, then I just take, I take k maximal such that all further coefficients are non-zero. So this is every polynomial can be written as a linear combination of the basis monomials. And, well, if some of them are 0, I just take k smaller than d plus 1. And if all of them are non-zero, just k is d plus 1, and I have the thing there. So all the alpha j's are complex numbers, and alpha k, the last one, is non-zero. So you can write P in this form. In my notes, P is F, but then I noticed that F is already an element of the Lie algebra. So the polynomial P is contained in W. So if I act with which one do I have to act? F and with E. By definition, W is a submodule, so if I act with E on the polynomial, this will be still contained in the submodule, and then of course I can iterate this. I can apply phi of E again to this element of W, and will still obtain a polynomial which is contained in W. So I do this k minus 1 times altogether. So let's think about this element. E was given by the action of E was given by the operator x ddy. So I apply this operator k minus 1 times to the polynomial P. First observation is that to the differential operator with respect to y, x is just a scalar, so I can pull out all the x's to the left. So this gives x to the k minus 1. These are just the x's which come from these operators. So now I have just ddy to the k minus 1 p. So let's study what this operator does to the individual monomials of this polynomial. For the initial monomials, all but the last one, the degree in y is smaller than k minus 1. Here it's 0, here it's 1, and here it's k minus 2, and then eventually the degree becomes k minus 1. So if I derive this k minus 1 times, almost all of the monomials will vanish, except the last one. Now, what happens with the last one? Well, alpha k is just a scalar. Then x is also just a scalar if I apply only derivative with respect to y. So I take it out and combine it with these x's and get x to the d. And y gives k minus 1 factorial. So, okay. So I've shown that this polynomial is contained in W. This is some non-zero scalar here, because alpha k was by assumption non-zero, and factorial is also non-zero. So also any scalar multiple of this, namely just x to the d, is contained in W. So far I've only used invariance under the operation of E. Now I also use the invariance under the operation of F. Well, same thing. X of d is contained in W, so phi of f applied to x to the d is contained in W. And if I apply it several times, then I still obtain an element contained in W. So what was this? E was x dy, so f is y d dx. And now I do exactly the same calculation as here. Now all the y's are just collected out on the left. And I get d dx to the j x to the d. Well, and this is y to the j, x to the d minus j. And here I have the product of all the integers from d down. So this is d factorial divided by, I think, j minus 1 factorial. Maybe it's, is that right? Did I say it? Yeah. Okay. No. So this is again some non-zero scalar. And by choosing suitable j, I can produce any of my basis monomials here, multiplied with some non-zero scalar. So W contains the basis of Vd. And then, of course, because W is a vector subspace, W is Vd. W coincides with Vd, which was what was to be shown. So we've seen that these are all irreducible. And in fact, on the next fourth exercise sheet, you have to do a very similar argument in number 1e. So you don't have to be as detailed as I'm here. So you can now, because this was the first time that you saw an argument like this, I was a bit detailed, but you can be a bit shorter. Yeah, that's it. Questions? Good. Then see you on Thursday. Yeah, good. Oh no, this was the new one. Chris, if you want to work on the exercises, also I recommend this, and you can, even though you don't come on Thursdays and you don't go for credit, you can hand in your solutions so I can give you feedback. And yeah, so I just wanted to let you know as a possibility. And also, if you don't hand in, I just encourage